Okay, all right. So welcome to this live on. Hope you can see the screen and hear my voice. Okay, so welcome to this live session on uh, 09. Okay, so 5 2026. Okay, so this will be like revision. So let's say quick revision. So quick revision of the concept. Okay. So before this end exam. Okay. So basically, let's go quickly one by one. So we'll have open loop. So starting of the problem. So open loop versus closed loop systems. Basically, what is the difference between open loop and closed loop? So the open loop, what we have is we have controller. Okay. So then you have reference input here. Okay. The controller will give you the control input. Okay. So that will be given to the plant or dynamical system. Okay. So we get the output. Okay. Whereas in the uh, closed loop systems, okay. So where we will have same structure of controller. Okay. So then we have control input. Okay. Then we have plant here. We'll have output. Yeah. Any doubt? Yes. Yeah. We will add the feedback. Okay. So uh, we'll have feedback here. So this is a feedback using the uh, measurement device. We also call them as the sensing device. Here we'll have the summing point, where this summing point we will use as a negative feedback. So that's why we have minus and plus. In case of if minus is replaced with plus, we call that is as a positive feedback. So this is same as the reference input. Okay. So in actual system, we'll have disturbance input here in the plant as well as the sensors also. Disturbance input. Okay. So basically, what are the advantages of the closed loop system? Advantages of closed loop system. So they are more accurate. They are more accurate. Okay. Less sensitive to disturbances. Okay. So less sensitive to the disturbances, less sensitive to parameter variations. Okay. Parameter variations. And we expect more oscillations. So tendency to oscillations. So these are the uh, major advantages of the closed loop systems. Okay. So this is the first topic in any of the control system course. Then we'll have the important topic called as the linearity. Okay. So basically what is linearity? So we could define the we could define definition with respect to a function. So a function f of x is linear. Okay. If it satisfies two conditions. So what are those? So first one is additivity. additivity. Okay, second one is homogeneity. Okay, where additivity we also call it is as the superposition. Okay, so how do you define the additivity? So you give both the inputs. So let's say x is the input here, output is the f of x. It is something like this. You give x to the system. Okay, something like this. You get output as f of x. Input is x, output is f of x. So when you give both the inputs, if you get outputs as summation of individual outputs, then we call that is as the system is additive, following additive property. Then homogeneity is when you give the input multiplied with some scalar constant alpha. Okay. So then if the output is alpha multiplied the output for all scalars. So for all scalars of alpha. Okay. Then we will say that system is linear. Correct? System is linear. This is the definition. Okay. So the example could be simple example could be if f of x is equal to 2x, is it linear or not? It's a linear. Okay.
It's linear.
Whereas if you take f of x is equal to 2x plus 9, is it a linear?
It's not. It's,
Non-linear.
yes.
Okay. So why? Because so that plus 9 will affect in the additivity property. Additivity as well as mostly additivity and homogeneity both. Correct. So that is the major important property in the because what we are studying is the LTI control systems, linear time invariant systems. Okay, so the linearity property is very important. Okay, that is second concept. Okay, then the third concept is the okay. Then the third concept is you should know what is the format of the linear dynamical systems. Okay, linear dynamical systems in general, because this system is a linear system. Okay, in terms of the equations, mathematical equation. But when you say dynamical properties, so you should define it specifically. Okay, this is how we define. So in general, if a system mathematical model is like this, a naught y of t plus a1 dy 1 of t by dt, sorry, dy of t by dt plus a2 d square y of t by dt square plus etc. plus an dn y of t by dtn equal to similarly b naught u of t plus b1 du of t by dt plus etc. plus dm u of t by dtm. If any system is in this format in terms of the differential equations, okay, in terms of the differential equations, then we could say that it is a linear dynamical system. It means that it will follow the previously defined the linearity properties. It means that we can verify both additivity and uh, the homogeneity property, this kind of systems. Okay, these kind of systems. Here also you can define some example. So example would be like 3d square y by d t square plus dy by dt plus 5y equal to 9. Let's say du by dt plus u. So is it a linear system? Yes, because it is exactly following the above format. Whereas if you consider this, let's say 8y d square y by dt square plus 2 dy by dt plus y equal to 3 du by dt, something like plus u. Is it a linear or non-linear? It's a non-linear. Why it is a non-linear? Okay. So because of this term. Okay. So if you simply verify both the properties of the linearity, that is additivity and homogeneity, okay, this system will turn out to be a non-linear. Okay. Where here, of course, in this equation, y is the output and u is the input. Okay. So these kind of systems you have already seen in the last weeks, final weeks, week 10, week 11. So the state space analysis. Whenever these kind of equations are given, we convert them into x dot is equal to x plus 3u. That we also
Yes.
called it is as a canonical form. Okay, canonical controllable form, CCF form. Okay, so these kind of linear dynamical systems we have. Then once the modeling part is done and put our equation system behavior into this linear dynamical systems equation, then generally what we do is to check its various behaviors. Okay, so we apply the famous transform technique called as this is for Laplace transforms. Called as Laplace transforms. Okay. So basically, how do we define Laplace transform? Given f of x, f of t. Okay. So the Laplace transform f of s is given as integral 0 to infinity f of t e power minus st dt. Correct? Where real part of s must be greater than or equal to 0. This is the definition. Correct? This is the definition. Then we
Yes, sir.
have, we might have seen different forms of Laplace transforms. Let's say sine bt, how much it is? So b by s square plus b square. What is the cos bt? So s by s square plus beta
Yes.
square. So what is Laplace transform of e power minus at? So 1 by s plus a. These are very standard. Okay. These are very standard, and we have so based on these, we have seen the properties of Laplace transforms. Okay, so what are various properties we have? So we have properties like linearity. Okay, then linearity property, I don't need to explain it to you. So then we have important property as convolution. Okay, what is this convolution says? If you define y of t as like this, g of t, let's say some other signal r of t, which are two signals, the convolution is defined with this star mark. So mathematically that is written as integral 0 to t z of t minus tau r of tau d tau, or integral 0 to t g of tau r of t minus tau d tau. Am I correct? Okay.
Yes, sir.
So if you apply the Laplace transform, it will turn out to be, so Laplace transform of output y of t will be equivalent to g of s multiplied r of s. It means that when two signals are convoluting in time domain, okay, they will be multiplying in the s domain. They will be multiplying in the yes domain. Correct? Where basically here, so in our basically what is the convolution? Convolution is nothing but okay, smoothing of one function over the other function. Okay. So basically, what is this y of s is? Y of s is the output. What is this g of s is? Transfer function. And what is this R of S is? Input, correct? Yeah. So based upon this, we could define our transfer function. Transfer function is going to be G of S is equal to the, so Y of S by R of S, correct? This is the transfer function. Okay. Then after learning about the these Laplace transforms, okay, so then we are entering into the important concept as transfer function. Okay, so transfer function is defined as, in general, okay, G of S is equal to some polynomial, numerator polynomial by denominator polynomial. Okay, generally we call this is as the so here the important condition is initial conditions are 0. Initial conditions are 0. Okay, so that means that, so we apply the Laplace transforms to this equation. Okay, using that Laplace transform of the higher order derivatives, there we will get the initial conditions. We take initial conditions 0 and finally find the expression of Y of S by U of S. Okay, so in general, we take these things as the proper Laplace transforms, correct? Proper functions. So proper functions. What do you mean by proper functions? Basically, the order of numerator is m, the order of denominator is m. So proper function means this m should be less than or equal to n. Okay. So in that case, we could write these things as some k multiplied s minus z1, s minus z2, etc. s minus zm divided by, so s minus p1, s minus p2, etc. s minus pn. Okay, where we call these zi as zeros. Okay, and these pi's as
Poles.
poles, right? So zeros and poles. Based upon the zeros and poles, so we can talk about the stability. Okay, that we know already, right? So in general, what is the structure we would have to talk about the stability? Okay, so we take this S plane. Okay, so we'll have real part of the S plane. Okay, then we have imaginary part of S plane, or we can also call it as the J omega axis. Okay, so you can have the poles location. Basically, we define the stability or behavior majorly with the poles locations. Okay, so we show the poles with the cross marks and zeros with the circles. Okay, so if you take up the poles at different locations, let's say here, 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 okay, and then here, here, okay, and then here, okay, here, and then here, here, different configurations. Okay, so how do the response would be like? This one will be like uh, pole is at s is equal to 0. Means what? How that function looks like? 1 by s, correct? So
Yes.
1 by s is the Laplace transform of the unit step. Okay. So what about this? Pole is negative value. Okay. Negative value means what? 1 by s plus a. Correct? So 1 by s plus a. How does the response looks like? The response would be like exponentially reducing. Correct? Right? Similarly,
Yes.
in the opposite way, how does the response here? The response would be
Right.
exponentially increasing.
Yes. Yes.
Okay. And uh, these two cases, okay, so the response would be like, so it starts somewhere Okay, so they starts exponential sinusoidally decreasing functions. Similarly, these two will be like, so they are just opposite. They are exponentially increasing functions. Okay, and these two would be like on the z omega axis. So their behavior is so exactly oscillating in nature. Correct. So basically, we'll have two parts. So LHS, J omega, and RHS. S-plane is divided into three parts. Okay. LHS, J omega, RHS. Okay. So where when the poles are in the RHS side, we say unstable region.
Yes, sir.
Okay. Stable LHS side, we say stable region. Okay. On the J omega, we say marginally stable.
Yes, sir.
Marginally stable. Okay. So based upon the transfer function, we define poles and zeros, and based upon the pole location, we decide the stability of the system. Okay. So that is another concept.
This kind of question will come in question paper, like graph
Sorry,
based, like this
sorry.
kind of 4-0 questions
Mm.
are coming in the quiz, like this graph, JMA question, and we have to,
Uh, your voice is not clear. What you are saying, your this kind of
this kind of question will come in the exam.
yeah, questions can be related to anything. They are just computer based, but they can be conceptual. They can be mathematical. Anything.
Okay, okay,
Okay, okay. So it covers all the concepts.
okay, sir.
Okay, then this is up to the applying the Laplace transforms. So then the next step what we have is time domain analysis. Okay, so in the time domain analysis, what we saw is we took the first order system. We took the first order system. Basically, first order system means what? So we have only one pole. So 1 by tau, S plus 1 by tau. Okay, so we'll have only one pole. It means that the pole in this case will be minus 1 by tau, minus 1 by tau. So that is how it will be like. Okay, so first order system. Okay, so in the first order system, okay, so when you take, let's say, based upon the input, because this is the transfer function, right? So transfer function is g of s is nothing but what? So output by input, output by input r of s. Okay. So if r of s is based upon the input, if r of s is the unit step, ramp, any other, we'll have different functions. For example, if r of s is equal to, sorry, r of t, r of t is impulse. Okay. Then what do you have? You'll have r of s is equal to 1. If r of s is equal to 1, what is y of s? Y of s is same expression. Okay, k multiplied 1 by tau, s plus 1 by tau. In that case, how that response would be like? The response would be like, so it starts at k by tau and it reduces. Okay, so we call somewhere this is as the time constant. Okay, so this is like some 0.37 k by tau. 37 k by tau. Okay, so this we call it as a time constant. Okay, similarly, if r of t is equal to something like u of t, then what is r of s is going to be 1 by s. Then y of s is going to be what? 1 by s, k, 1 by tau, s plus 1 by tau. Correct? So if you can find the y of t expression, if you find the y of t expression from here, okay, it will be like increasing function. Okay, so you'll have this k here. Then time constant in this case would be like 0.63k. This is the time constant. Okay. Here in this case, you'll get y of t as the k e power minus t by tau. Here you'll get y of t as the k 1 minus e power minus t by tau. This is first order system behavior. Is it clear? Right? Then,
Yes, sir.
yeah,
Yes.
then we'll have in the similar way second order system. Okay, so second order system. Okay, in general, second order system would be defined like some A2 y double dot A1 y dot plus A naught y equal to B naught R, where y is the input, R is the output. So if you take the Laplace transform and find out g of s, which is nothing but y of s by R of s, you will get this one like B naught by A, B naught by A2 divided by s squared plus A1 by A2 s plus A naught by A2. Okay, here you'll see you'll have two poles. Okay, so P1 comma P2, two poles. So if you apply that b square minus 4ac principle, so you'll have minus a1 by 2a2 plus or minus root a1 by 2a2, okay, minus, so b square minus 4ac, something like a naught by a2 you will get. Okay, so minus b by 2a. Yeah, yeah. This is something like this. Okay. So then based upon this, okay, if you take up, let's say some R of t is equal to, uh, here, this is the entire behavior for R of t is equal to delta of t. Okay. So then based upon the, this particular term, okay, you have three cases. Okay. First one is over damped. Okay. Second one is under damped. Third one is the critically damped. Okay. So what do you mean by over damped? Whenever this A1 by 2 A2 whole square term is greater than A naught by A2. Okay. Just a minute. Okay. So in this case, you will get the response like y of t. Here, what do you what did you get? So you will get your zeta is greater than 1. Okay, so you'll get the response as k1 e power at plus k2 e power uh, uh, sorry, k1 e power t1t plus k2 e power t2t. Okay, then here under damp, so the value will be zeta is less than 1, less than 1. So you will get like a1 by 2a2. I think here we will have square. Okay, so square is less than a naught by a2. Okay, here you will get y of t as b naught by uh, 2 a2. Okay, e power minus t by tau sine omega dt. Okay, here critically damped, you'll have zeta as 1. Okay, so here in this case, a naught by 2 a2 whole square should be equivalent to a naught by a2. Okay. In this case, you'll get y of t as, okay, b naught by b2 t e power minus t by tau. Okay. So finally, what we get here is, okay, what we get here is, okay, so this response you will get in this form. G of s is equal to, so k omega n square divided by, so s square plus 2 zeta omega n s plus omega n squared. Hope this is clear.
Yes, sir.
Okay, so this will be the general format. Okay, this equation you can write to replace the numerator with omega n and denominator with these corresponding terms. So this will be the format. This will be the format for the transfer function. Okay. So once you have this, so what you can do is you have both now first order system and second order system. Okay. So you can find the performance. You can find the performance. So let's say performance in the first order system. What do we have? Performance of first order. Okay, for R of t as the U of t. Okay, similarly, you have, I'll take that one later. Okay, so here what we do, so you have your transfer function. Okay, so G of s as y of s by R of s equal to k 1 by tau. Okay, so s plus 1 by tau. Okay, so here we are saying R of t is the u of t, R of s is 1 by s. So if you substitute and find y of t, okay, you will get something like k 1 minus e power minus t by tau. Okay, this is the function. Okay, so this function, so if you plot it, okay, this is y of t, this is t. So this function would looks like this, exponentially increasing function. Okay, where this will be like k. Okay, so then you will have, so you will have, if you draw the response something like this, where this is the slope dy by dt at t is equal to 0, with the time t is equal to 0. So wherever it intersects, wherever it intersects, okay, so we take that is as tau. We take that is as tau, and this will be like 0.63 k. So time constant is the tau. Time constant is the tau. Okay. Here basically when you substitute, okay, that is first case. Okay. Then you will see here this time. Okay. So 0.1 k. That means 10% of the k to this time. Okay. 0.9 k. 90% of the k. Okay. These two times, the overall time, we call that is as the rise time. We call that is as the rise time. Okay. So rise time is TR. So that will be like, if you do the calculations, like 0.1 k to zero point 0.9 k, you'll get rise time as 2.2 tau. Similarly, settling time, so TS, that will be like, so the time for that is nothing but time for reaching 2% or 5% tolerance of the final value. Of final value. Okay. So y of infinity is the final value. For any function, final value you can find by using the final value theorem from the Laplace transform. Okay. So that will be like 3.9 tau or 3 tau. So that means whenever it is the tolerance is 2%, the settling time is 3.9 tau. When it is 5%, 3 tau. Okay. So that's it. Okay. So that is for the first order system, finding the rise time as well as the settling time. Okay. Similarly, performance indices, okay, we can find for the second order system. So performance of, okay, second order system. Same for R of t is equal to U of t. Okay. So now what we have, y of s by r of s, which is nothing but the transfer function for the second order system. We have seen just now. Okay. K omega n square by s square plus 2 zeta omega n plus omega n square. Okay. Now if you, in this, what is r of s? R of s is going to be 1 by s. If you substitute it, okay, and take the Laplace, you'll get the y of s expression. Okay. And take the Laplace transform, inverse Laplace, you'll get y of t. That will be like something like 1 minus, what do we have? I don't remember this exact definition. 1 by 1 minus root square. You'll have exponential term. I think zeta omega n t. You'll have some cosine term, omega dt minus phi. Yeah, I think this should be correct. Please verify this. So that is the y of t expression. Once we have this y of t expression, again, we can draw this time response. Okay. We can draw this time response where this is nothing but, so 1, because R of t reference input is 1. Okay. So then the response would look like this. Okay. The response would look like this. Okay. So now again, just like the previous way, we could have 0.9 final value, 0.1 final value to define the rise time. So this will be our rise time. Okay. Similarly, we could have this time to reach first peak. This we call it is as the peak time. And this magnitude we call it is as the peak overshoot. Okay. I think it is clear. Then we'll have two times. Okay. So this is the 0.02. Okay. Plus or minus. I told you 2% tolerance. This is as 5% tolerance. This is 2% and this is 5%. Okay. So these are the things. So the time to reach this value is nothing but the settling time. Time to reach this value is nothing but the settling time. Again, if you see these values, maybe expressions, the rise time will be like approximate expressions. 2 omega n, peak time would be like pi by omega d. Okay, then settling time would be like approximately 4 time constants. Then peak overshoot would be like e power minus pi zeta by 1 minus zeta square. Okay, percentage overshoot. Okay, these are the different performance characteristics for second order system, and these are for first order system. Okay,
Okay, sir. So
yeah,
there is a y of t expression, the
yeah, yeah,
following.
yeah, yeah.
There should be cos omega d minus phi or plus phi.
That I'm not sure. Please kindly check it once because
But
I,
in my book it is
yeah,
plus
yeah.
phi.
Oh, it is plus 5. Okay.
Yes, sir.
Yeah. So please verify it. Yeah.
Okay.
So then after this, we'll have these after performance techniques, we have these block diagram techniques also. Okay, so we'll have let's say 7. So block diagram reduction technique, because uh, generally if you consider any plant, okay, so let's say take a some chemical plant. The chemical plant will have different smaller components, different smaller components. To find the overall transfer function, so uh, first we have to find the transfer function of individual components and try to reduce them by adding one by one. Then finally we find the overall transfer function. Okay, so that's where this block diagram reduction technique will be useful. Okay, so first thing is, let's say you have uh, uh, first let me discuss the first one. Okay, whenever you have the negative feedback means I told you. So the closed loop system, you have negative here, the below one. You have controller. Okay, you have plan, you have output, you have response, and you have edge. Okay, so in general, okay, so the transfer function for this is defined as, without the c, that will be like g by 1 plus gh. Here we are saying it is the negative feedback. Okay, whenever it is positive feedback, if there is a plus, so we will get minus here. Okay, so
Okay.
positive feedback and negative feedback. Okay, so that is how you will reduce whenever you see this structure like this. Okay, so the y by r response would be like this one, g by 1 plus gh. Okay, so always to reduce the to reduce the block diagram, always you make sure that the final the term should be same. For example, let me explain here. You'll have z here. Okay, then you'll have a summing point, let's say plus and plus. You'll have a, you are giving the b here. So in general, what do you get here? You'll get a plus b, correct, right? Okay, here you'll get a plus b multiplied b. Okay, now my intention is, okay, move the summing point from before g to after g. Okay, that's my intention. Okay, so what is the change I need to do? Okay, what is the technique I need to do? Okay, only thing is that what we need to make sure is that after transfer, after shifting of this summing point also, the overall transfer function, that means overall response, that should not change. Okay, if we make sure that that is not changing, then whatever you are doing is correct. Okay, so I'll let me show you that how to do that. Okay, so first let us start with the final expression. What is our final expression? So a plus b multiplied z, correct? That we wanted to make sure. I need to get the same expression. Okay, so let's write down that as something like az plus bz. Okay, now what is your intention? Basically, your intention is to shift this one here and your z should be here, correct? That is your intention. Okay, so that has to be plus plus and g. Okay, so that we wanted to make sure. Okay, now you see here, what here you wanted to get, here az plus bz. Okay, now already you have z here, so put a here and take one more z here, put b here and add that one here. Now you can see that. So you got AZ plus BZ is equal to A plus BZ. Now so the summing point has been shifted from back of this transfer function G to front, backside to front. Okay. So that's how the block diagram technique will work. Okay. So you can have the other, we can have different steps also. You can also follow the same. Okay. So it will gives you an advantage. Okay. Uh, Next, what we have is based upon the block diagram, and we have three definitions for stability. Let me explain those also. So, stability of linear systems. Okay. So, we have natural response. Okay. Then we have stability. Then we have unstable. Okay. Then we have marginally stable. Okay. So basically, um, the natural response is nothing but the response or output to due to output to due to output due to any input. Okay. Sorry. Output due to uh, output due to not any input, but with only initial conditions. But with only initial conditions. Is this clear? That is called as the natural response. We should not apply any input. So system response only due to the initial conditions. Okay. Then stability. The
Sir,
stability is, yeah,
one second, sir.
yeah.
Natural response.
So natural response in the sense, let's say you have this AX, X dot is equal to AX plus BU. Okay. You take
Okay,
this
sir.
input term to zero. So this term goes to zero.
Okay, sir.
Okay. Then you have only X dot is equal to AX. What is the X? What is the solution for this? X of t is equal to e power minus AT x of 0. Correct?
Yes, sir.
Now only initial conditions are acting.
Okay, sir.
So find the draw the response for x of t, which that is nothing but the natural response. Okay. Then stability is nothing but natural response approaches to zero. Natural response approaches to zero as t is tending to infinity. It means that if you consider this response, okay, so if it is like this, it starts at x of 0, and if it goes to 0 as t is tending to infinity, then we say that that system is stable. Okay. Then unstable is same natural response. Okay. So not approaching to 0, but grows without bound. Without bound as t is tending to infinity. It means that same x dot x of t is equal to e power minus at x of 0. It starts at x of 0. Instead of going down, it increases like this without bound. Is this clear? So we are talking about natural response only, not with any input. Okay. Then marginally stable, same natural response. Okay. Neither grows. Okay. Nor approaching to 0. approaching to zero as t is tending to infinity. Okay, so that we call as a marginally stable. Generally, those the response would looks like this. It will not increase or it will not reduce. Okay, so in our these are the general definitions. Okay, using poles. Okay, this is nothing but all poles must be on the LHS side. This is nothing but any one pole on the RHS side. This is nothing but any one pole on the J omega axis. Is this clear? So using poles, we can define these three terms. Correct? Yes or no?
Yes, sir.
Yeah, yeah. So, but the basic definitions are these with respect to the natural response. Okay. Then, so then when it comes to the stability, okay, when it comes to the stability, we have read this Routh-Hurwitz criteria. Routh-Hurwitz is stability criteria. Okay, so Routh-Hurwitz stability criteria will say that when we apply this Routh-Hurwitz stability criteria, so uh, you have this closed loop transfer function. Okay, so whenever you have closed loop transfer function, something like n of s d of s. Okay, so we take the characteristic equation. The characteristic equation is d of s equal to 0. If d of s is order is greater than or equal to 3. Why greater than or equal to 3? If it is up to 3, we can directly find the roots and we can place the roots on the S plane and we can check whether any root on the right side or not. Correct? But if order of that d of s equal to 0 is greater than or equal to 3, okay, it will be very hard to find the poles directly. Very hard to find the roots directly. Okay, in that case, the Routh-Hurwitz criteria is going to be useful for us. So in the Routh-Hurwitz criteria, what we do first step, we form this Routh table, correct? I'm not explaining how we are forming the Routh table, okay? So we form this Routh table, then we check what? We check the first column, correct? We check the first column, okay? So if first column has same sign, all the terms are same sign, then we say that stable. If there is a sign change, then we say that system is unstable and number of sign changes equal to the number of poles on RHS side. Correct? Number of sign changes is equal to the number of poles on the RHS side. Then in the same RH table, we'll have two special cases. You remember those special cases? Okay, what is the first special case? What is the first special case? So in the first element, okay, so is 0. First element is 0. If first element is 0, what happened? So later we get the situation of undefined, correct? Infinity case. We'll get the situation of undefined case. In that case, what we do? We replace with epsilon, correct? We replace with epsilon and continue the calculations. Okay. Then take limit epsilon tending to 0 and decide it. Okay. That is one case. Second case is all numbers. All numbers, okay, in a row or 0. In a row or 0. So in this case, what we do? we take something called as the auxiliary polynomial. Auxiliary polynomial, take the derivative and replace coefficients. Replace zeros with those coefficients. Zeros with those coefficients. Okay. Then continue the calculations. Correct? That's how we will do. Okay. I hope this is clear. The Routh-Hurwitz criteria. Okay. Then, so we could use this Routh-Hurwitz criteria. Okay. We could use this Routh-Hurwitz criteria. So in the functions, in the block diagrams, let's say we have this uh, controller K1, the plant V1, let's say feedback V2. Okay. So we have something like this. Okay. So plus minus, you have R, you have Y. Okay. You can find Y by R where K1 is going to be the parameter inside. Okay. So you can use this RH criteria to decide the range for K. Range for K for the system to be stable. You can find that range. Okay. So that is the advantage with the RH criteria. Okay. The next, what we have is the feedback control. So feedback control, when you see the closed loop system, you have controller, okay, you have a plant, then you have feedback here. So then this is the summing point. You have reference input R, you have output. Okay. So basically, feedback controller, what it does, we have seen the closed loop system advantages. Okay, so advantages are like when we keep the feedback, so response will be faster, it will be better stable, less sensitive to the parameters, and so there is a possibility of getting the oscillations. Okay, so suppose if you replace this C with K. Okay, that means proportional controller.
Sir, when class started?
4 o'clock.
4 o'clock. But
Yeah.
it is given that the class will start from 5 o'clock.
No, it is mentioned on the screen.
Sorry.
Mail
There is a
came.
no, there is a class at 5 o'clock also. So we will continue.
Yeah,
We will
five
finish this
o'clock.
record.
Vasumati will continue. So from this basic
But mail
concepts.
came that timings is 5 to 6. That's why I open in 5 o'clock. But class is continuing from
Where
first.
did you saw that?
Mail came to me.
Yeah, sir. Mail. We have got a mail
Oh,
also
we
that.
got a mail yesterday, sir.
Mail.
Yes, sir.
Yes.
Uh, Office
Yes.
people have mailed Chakravarti.
Sorry. Office people.
Office people have mailed. Yeah.
Oh, okay. But afternoon 2 o'clock, I've sent a message also on the Discord saying that 4 o'clock, the live session starts at 4. You should have seen that.
No, I
Today
We are
afternoon
sorry
also
about
I've
that.
sent a, yeah. Afternoon also I've sent a message.
Sir, where?
So please avail the recording as soon as possible so that
Yeah. So I'll upload
yes,
it.
recording. Yes, sir.
Vasumati, can you continue from here?
Yes, I'll do. Yeah.
Yeah.
That's why I
So I'll
joined. Yeah.
upload this. I'll upload this video by maybe in half an hour itself. We
Sir,
can
please,
watch the
please,
this.
please.
Yeah. So Vasumati will continue from here, the feedback concepts onwards. Okay.
Sir,
All
this
right.
video will also be available on YouTube, right?
Yeah. Sure. I'll upload in half an
Thanks.
hour.
Thanks.
We hope we'll get the video. Yeah. Sure.
Okay, okay,
Vasumati, please
okay.
take over.
Yes, I'll take it. Those who attended the previous session, anybody needs any 5 minutes break? If so, I'll